Welcome to our discussion on the area problems, which is really our beginning discussion on integrals. Previous lessons we've used tangent and velocity problems to introduce the idea of a derivative. And the derivative is the central idea in differential calculus. Now, in much the same way that we did that, we're going to start our discussion of integration by looking at area and distance problems, and then see that we can formulate the area of a definite integral, which becomes the basic concept of integral calculus. And so this is kind of the delineation between differential calculus and integral calculus, i.e. taking derivatives and then taking integrals. And we will see that the connection between integral calculus and differential calculus is shown with the fundamental theorem of calculus, which relates those two things together. And there are other videos that will help explain that concept later. But for now, let's start with the basic idea of a definite integral by starting with area problems, or area under a curve. So if we had a straight line, if instead of a curve this was the constant function, right? This was just the function y equals c for some constant, and then we wanted to find the area under the curve from A to B, that would be very easy because it would be a rectangle, and we could find the area of a rectangle as base times height. Very simple. But what happens is, what do we do when we have a function that's no longer a constant function? When we have this regular curvy blue line function instead, and we want to find the area under that curve. Well, it's going to come down to, we can approximate it with a bunch of rectangles under the curve. You get the idea. We keep going, and then of course you can see, oh, look at all this error, right? All of this that's not being counted. So then we can take our rectangles and make them thinner, kind of cut them in half. And now you can see that we gained this. This is no longer error because we're now seeing that. And if we cut this one in half, envision this one going all the way down, then we gain that much. If we cut this one in half, we now gain that. And you can see how as we get smaller, right, thinner and thinner rectangles, this approximation is going to get better and better. And that's basically where we're going to be heading with these ideas. Okay, so as I said before, if we're trying to find the area of a rectangle, it's very easy. We can do length times width. We can also cut it up into other shapes. We can look at area of triangles and polygons and all that kind of stuff. But it's really going to be easiest if we just stick with rectangles. So the first thing we're going to do whenever we're trying to find the area under the curve is we're going to approximate that area with a bunch of rectangles. So let's take a look at a simple example. Our friend the parabola, right? Y equals x squared. And we're just going to look at the portion of x squared from 0 to 1. And we're going to look at the area under the curve. So basically between the function y equals x squared and the x-axis. So that little blue triangular shaped region, we want to know what's that area. Well, we could approximate it by one curve, right? We could do a triangle, and then there's our base, there's our height, right? So a base of 1, a height of 1, and that area of the triangle would be 1/2 base times height, or 1/2. Or we can cut it into these pieces here, and then we could do a bunch of rectangles and add those up, and then maybe even connect the dots, right, and get a bunch of triangles and do all of those. And there's all sorts of different things we could try geometrically to try and figure out the area under this curve. However, the easiest thing, rather than trying to do a bunch of rectangles with triangles on top of them, the simplest thing is to just stick with rectangles. So we can approximate the area of the curve with these 4 rectangles. As you can see, it's a pretty bad approximation, but you got to start somewhere. So you take your range, right? Let's call it an interval instead of a range. So you take this interval from 0 to 1 and you cut it up into however many equal pieces you want. So you're going to start with 4 equal pieces. So you take that distance of 1, you cut it right by 4, and you get 1/4, and then 2/4, which is 1/2, and then 3/4, and 1. So there's your cutoff points. Then you basically do rectangles up to the curve. Now you can see in this case we're doing what are called right hand or right endpoint rectangles. Right? These are right endpoint rectangles because you'll notice that if you go to 1/4 and you go up and where it touches the curve, that's where you make that first rectangle, right? And then if you go to 1/2, here's my second rectangle. I could have stopped it at the left hand point and then it would have been the same height as this one. Or I could stop at the right end point and it goes up there. Now you can see that because we have a constantly increasing function, and this only happens for constantly increasing functions, by the way, so don't think that this pattern always holds, that in this case, because we're doing right hand approximations for all of these, they all overestimate, right? But if we did left hand approximations, well, this first one would be 0 because the left hand height would be nothing, and then the second one would be this, right? The third one would be that, and the fourth one would be that, which you can see would be the exact same area that you get from these 3 rectangles. So all that's happening is you're losing this area of this large one. So the right hand rectangles are a very obvious overestimate, and then these left hand ones, right, which would be everything shaded here, you can see would be a huge underestimate. And then of course you could take the average of the two and that would be an even better estimate. You can also do, which we'll see another technique is, instead of doing a right hand estimate or a left hand estimate in red, you can do the midpoint estimate where you go to the middle of each of your little intervals and you draw a rectangle based on the height of the function at that midpoint. And you can see that that's a better estimate because in this case you have an underestimate, right? We're not counting that area, but we're overestimating that area, and hey, those might kind of even each other out. But again, that kind of evening each other out idea really only works here because we have a function that is always increasing, right? Its concavity hasn't changed. So we'll stick with the simple one for now, and we'll look at what happens with right endpoints and left endpoints. So this right endpoint one, if we wanted to calculate those heights so that we could calculate those areas, you can see that it's just going to be the function evaluated at these points, right? This first rectangle has a base of 1/4 and a height of f of 1/4. So you would plug 1/4 into x squared and you'd go, that's a height of 1/8, right? Because, sorry, 1/16, duh, because it's 1/4 squared. And then the next one, you would do f of a half, right? And you do 1/2 squared, which is 1/4, and that would be the height here, so it would be 1/4 times 1/4. That'd give you the area of that one. Next one, 3/4 squared, or 9/16, right? And this last one, 1 squared, which is 1. If we sum up those areas, and if we write it all out, you'll kind of see a pattern. 1/4 times the function evaluated at that first endpoint, which is 1/4, plus 1/4 times the second endpoint, 1/4 times the next one, 1/4. You notice how they're all being multiplied by 1/4 because all of those are the widths of each of those rectangles. Add it all up, you get 15/32, or basically 0.46875. Now remember, when we did our triangle, we got an area of 1/2. So this one is pretty similar to that. We also can see that the area, and I'll bring the picture back up, we can see very clearly that the true area is going to be less than whatever we just found. So we know the true area has to be less than 0.46875. Well, as I said, we could also try it the other way. and do left endpoints, use the left endpoint method, and create the rectangles from the left endpoints. And then add all those areas together. And again, 1/4, because that's the width, right, times the height. 1/4 times the height, 1/4 times the height, 1/4 times the height, add it all together, you get 0.2. And as we see very clearly from the picture, that is an underestimate. So we know that the true area we're looking for is somewhere between this 0.22 almost, right, 21875, and 0.4 almost 7, right, 46875. So somewhere between those two is the actual area. And then we can repeat this process with more and more rectangles, which will give us more and more accurate approximations because the error, right, of each rectangle is getting smaller and smaller each time. And by doing this, like for instance, if you did the math with 8 rectangles, you now get this closer approximation. So now we're narrowing that window down. It's somewhere between 0.27 and almost 0.4. And then we can keep going and keep going. And this is what happens as you keep going and keep going, right? You now, n here represents number of rectangles. So now if you take that that overall interval of 0 to 1 and break it up into 10 pieces, here's your left and right approximations. And you can see that these numbers, right, the area kind of in between the two, they seem to be approaching a certain thing, and it looks like it's going to be about 1/3 each, right? I mean, look at what's happening with 1,000 strips. It narrows it down to 0.32 blah 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 blah, 0.33 blah blah blah. It's getting really really close to roughly 1/3. Right? I know here we wrote it with ended with a 5 because they both ended in a 5, but you can really think of this as pretty much being 1/3. So that's going to be a pretty good guess, but you know, how many people want to try and calculate 1,000 of these little rectangles? There are programs that will do it for you, but it would still be a big pain in the butt. There's got to be a better way. Well, here's a visual approximation of what's happening. And you'll notice that as we do more and more rectangles, what's happening to the width? It's getting thinner and thinner, right? The width of each rectangle. And if you'll remember from how we calculated these things, it was width times the function evaluated at that height, and this width is getting closer and closer to 0. So you're basically summing up a bunch of things and letting one thing get closer and closer to 0. We also saw that as the rectangles got thinner, i.e. as the numbers went up, the right-hand answer and the left-hand answer were getting very similar, right? They were getting much, much closer to each other. So we have kind of a left-hand limit and a right-hand limit that are approaching each other. And they're approaching that number, and we already said that that number seemed to be approaching 1/3. Okay, so what happens if we want to do this with a function that isn't necessarily one concavity, that it's not always increasing or always decreasing, it's wavy like this one? Well, the idea is still sound. You can still take your interval from A to B, break it up into a bunch of subintervals by just dividing it by how many you want to do, and the size of each of these rectangles, right, the width of each of these is going to be uniform, and it's just going to be the overall interval, right, this overall length, which is just b minus a, divided by n, right? Because if you wanted to go from, let's say, 3 to 10, isn't that a distance of 7? Yeah, 10 minus 3, right? So you take the overall distance, divide by how many intervals you want, right? How many rectangles you want, and that gives you the change in x. This is your change in x. It gives you the width of each rectangle. So we're starting to generalize now. Okay, so these intervals can all be written as going from x sub 0 to x sub 1, and then x sub 1 to x sub 2. These are just fancy ways of saying we start at the first number a. We're going to call that x sub 0. That's going to be our first 0, our null our first x, that's our starting x, and then each cutoff, right, each delta x, each change in x is just going up to the next one. So then we go up to x1, then x2, and x3. But again, instead of using all those subscripts, we can just think about it as, hey, this x1 is just our starting point plus this delta x, whatever this change in x was. And this next x2 is just a plus 2 of them. All right, go back and look at the picture. Each one of these is a delta x. So x3 is just a plus 3 delta x's, whatever this delta x is, right? So let's say it's 1/10. Then this is 1, 2, 3/10, right? This number here is going to be 3.3 because it's going to be 3 plus 3/10, and this is going to be 3.4, 3.5, etc., 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 all the way up to b. Now, obviously, it's not it's not a tenth because if this is a whole distance of 7, but you get the idea that each new x is just a, our starting point of our interval, plus a certain number of changes in x, a certain number of delta x's. So we can kind of generalize it that way, that these endpoints, these second numbers, instead of calling them x sub 3 and x sub 2, we can relate them all back to an a and a delta x, because it's nicer to have everything in terms of one thing rather than all these different x's to worry about. It's going to make the math a lot easier to generalize. So if we want to now approximate the ith strip, that just means pick a random strip between the first and the last, and we'll call it the ith, right? This is the x sub 1, this is the first strip, second strip, third strip, da, 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 da. This is the ith strip. It means it's I many places over. Again, because we're just trying to generalize it. We know the area of that ith rectangle is just going to be the function evaluated at the right-hand endpoint, because we're just doing right-hand endpoints right now. This is for right-hand sums, right? That's what r sub n means. It's just we're doing right-hand sums. If we were doing left-hand sums, it's going to change slightly, but the idea is the same, so we can generalize from just doing right-hands. Okay, so again, the ith strip, then we're going to take the height at x sub I, so that's f of x sub I, right? Because the height is just the function evaluated at x sub I, so it's just the function evaluated at this point, whatever that number happens to be. And then the width is just this delta x. And then we can see, hopefully intuitively, that the sum of all of those rectangles is just the f of each right-hand endpoint, right? So f of x sub 1, f of x sub 2, f of x sub 3, dot, 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 all the way up to f of x sub n, n being the last one, right? Each of those heights times each of their widths, where the widths are all delta x's. And so if we have 2 of them, 4 of them, 8 of them, 12 of them, we can see what the picture looks like. And then the idea is to try and figure out what's the pattern as we let n, the number of rectangles, go to infinity. What happens? Well, we get this lovely thing, that we know the area is going to be the limit as n goes to infinity of this kind of finite sum of these right-hand rectangles. And if we kind of sub back in what the formula is, then that's just saying we're taking the limit as n goes to infinity of f of x1 times delta x plus f of x2 times delta x, dot, 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 right, all the way. So we're just saying that if we want to find the area, we're just going to add up all these rectangles, and we're going to let this sub n go to infinity. So we're going to have an infinite number of these rectangles. And then we can see that if we want to do the left-hand sum, right, the left-hand rectangles, that all that changes, think of it this way. Let's look at this one. We'll look at 4. Our first rectangle, if we're doing a left-hand rectangle, is this one, because the left-hand rectangle uses the left-hand height of the function, and then this would be our second rectangle, and this would be our third one, and then this one would be our fourth one. And all that changes is to find the area of this first rectangle. Instead of using the height of the function at x sub 1, we're using the height of the function at a, which is what we would call x sub 0. And then to find the height of this second rectangle, instead of using the height at x sub 2, right, because we don't want the right hand height, we want the left hand height, so we're using the height at x sub 1. So we're doing f of x sub 0 to get this height, and we're doing f of x sub 1 to get this height, and f of x sub 2 to get that one, and so on and so forth. So you can see that if we generalize that, this first height, instead of being at x1, it's at x0. And then this second rectangle, instead of being the height at x2, it's the height at x1. And then when you get to the end, instead of the last height being the last number being x sub n, it's x sub n minus 1. Again, take a look at this picture. Instead of it being x to the fourth, it's x cubed for the last one. And that if n is 4, then we're doing 4 minus 1 is 3, right? If we're down here, instead of using this last one, this very last piece right there, we're using this one here. So if that's n plus 1, and then we're getting that rectangle, the taller one. Okay, so that's all that's happening with these two formulas, is we can see that they both give us basically the same thing. Okay, and in fact, we can prove this, and we won't do it here, but you can prove that these limits will approximate, or I'm sorry, approach the same thing, whether it's the left hand or the right hand, and it will also work if you just pick any value inside the interval. And that's what these little asterisks mean. It means instead of pigeonholing ourselves and saying we must pick the left hand value of our little interval and then do the height of that, or we must pick the right hand interval and then do the height there, this general expression, this kind of theorem idea says we can really just pick any number anywhere in this interval and let the height of the rectangle be the function evaluated at that point. And it doesn't even have to be the middle, it doesn't have to be the same in each one, right? So we let our first point be pretty close to the beginning, the second one is almost in the middle, the third one is a little bit more to the right, this one looks like it's close to the middle, close to the middle, close to the middle, so on and so forth. You can pick any x value anywhere in this entire interval and it doesn't matter. And think about this intuitively. Why does this not matter? Well, remember, what are we doing? We're taking the limit as n goes to infinity. As n goes to infinity, these rectangles shrink. They get thinner and thinner as n gets bigger and bigger. And so if you started here or here, right, if you started with a right-hand endpoint or a left-hand endpoint, as these things shrink, these two endpoints come closer and closer to each other. And if you decided to start here, right, some value in the middle of your endpoint, again, as the rectangles thin, as the two sides shrink towards each other, then all three of these points end up getting swept together and they end up becoming the same thing. So it doesn't matter what you choose. As you let that delta x go to 0, which is in essence what happens, as n goes to infinity, the size of each rectangle goes to 0, and the left hand, right hand, and any point in the middle end up becoming the same darn point, because what happens is you end up getting an infinite number of these rectangles of no width, right? They end up becoming kind of a line, and you think, well, how the heck do we find the area of a line? Well, geometrically we don't, but using calculus we can, and that's the beauty. Okay, so this is just some verbiage talking about how this all works, right? That if A is the unique number that is smaller than the upper sums and bigger than all the lower sums, then we can find that area. We know that it's trapped in between those two, and we see that those two limits, the left and the right, end up approaching each other, and it's kind of like that squeeze theorem idea, that because it's squeezed between these two things, that we know that it has to approach that same number, and we can actually find that area that is between those two approximations. And here's a visual of what's going on that we've already seen. The right hand and the left hand sums were both seeming to approach point 3. Here's the right hand ones, here's the left hand ones. But in general, when we have functions that aren't constantly increasing or constantly decreasing, and in the case of x squared, right, we had a function that was constantly increasing. When we have things that have curves, then in general we can form lower and upper sums not by always choosing right hand sums or left hand sums. We have to instead choose our numbers appropriately, right? So for instance, the lighter blue rectangles would be our upper sum, and we can see that we can create an upper sum by, in this rectangle, choosing the left hand endpoint. In this one it's the left hand endpoint, but in this one it's the right hand endpoint. In this one it's some point in between, because we had to pick, right, we had to make it maximize itself up here, and then for this one it was left hand endpoint. And then to get the darker blue ones, to get the lower sum for this first interval, we'd have to pick a right endpoint somewhere in the middle, left endpoint, left endpoint, right endpoint, right? So we can always calculate a lower limit and an upper limit of these sums by allowing ourselves to pick any number we want, right? Any place that we need to be in each of the rectangles. Sometimes it's the left endpoint, sometimes it's the right endpoint, sometimes it's in between. But we've seen that as n goes to infinity and these rectangles shrink, those points all go to the same place. So as we've seen from these examples, we have to add up a bunch of areas of rectangles. And we need to come up with a simpler way of describing these sums. So we're going to use sigma notation. It's just a shorthand notation that allows us to designate a sum without having to write all that stuff. So you'll recognize here on the right hand side, this is just that sum that we've seen in our previous equations, equations 2, 3, and 4, that talked about right hand, left hand, and then the kind of somewhere in between point sums, where we took the function evaluated at x sub 1, multiplied it times its delta x, then we added that to the function evaluated at x sub 2 times delta x plus dot 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 right all the way up to x sub n. Well, this sigma notation, sigma being this Greek letter, it looks like a big capital E, sigma for sum. This notation just means let I start at 1 and end at n, and you're going to do whatever it tells you to do here once when I equals 1. Then you're going to add that to the same thing done when I equals 2, add that to when I equals 3, right? So it says take the function evaluated at x sub I and then multiply that by delta x. So you take the function, you evaluate it at x sub 1, multiply that by delta x, then add that to the function evaluated at x sub 2 times delta x, added to f of x sub 3 times delta x, so on and so forth, all the way up to x sub n. It's just a shorthand notation, so we don't have to write out all this crap every time. And you'll notice that this here, right, was our right hand sum, this was our left hand sum, and this was the I don't know, I forget what we called it, it was just the x asterisk sum. So here we do x sub I and we let I go from 1 to n. Here we have to do x of I minus 1 and let I go from 1 to n, because if you'll remember for this one, when we did the left hand sum, the first x we did was x sub 0, and the last one we did was f of x of n minus 1, right? So in order for this to happen when I goes from 1 to n, we have to do I minus 1, and then I minus 1 gives us n minus 1 at the end. You could also write this as just f of x sub I, just like this one, and then all you would do is change this to go from 0 to n minus 1. There's no rule that says your summation always has to go from 1 to n. You could always change your summation endpoints and then not have to change this syntax. So either one would work, right? Just keep that in mind. Okay, so we've talked about area under a curve as being the first problem that we're going to try and fix or figure out with integration integrals, the definite integral. What about the distance problem? So what if we want to find the distance traveled by an object during a certain time period if the velocity of the object is always known? Well, if the velocity was constant, then the distance problem would be very easy because we know distance equals rate times time, or distance equals velocity times time. And if velocity was constant, then we could very easily just take that constant, multiply it by the length of time, and bingo, bango, bongo, there's our distance. But what happens if our velocity varies? Because as we know, there are many things in the natural world that do not have constant velocities. So it's going to be important to be able to model those things or figure out the distance traveled by something that didn't have a constant velocity. Well, suppose the odometer on your car is broken, right? And so we don't know how far we've traveled, right? That's what the odometer gives us. But we want to estimate our distance driven over a 30-second time interval. We can do that by taking speedometer readings. We can figure out how fast we're going every 5 seconds, record those in a table, and then we can figure out distances over those little time intervals, right? So starting when we first start the stopwatch, time equals 0. We're traveling at 17 miles per hour. After 5 seconds, we're up to 21, right? At the 10-second mark, we're now traveling at 24, 15-second mark, 29, so on and so forth. Obviously, we're in no hurry to get wherever we're going. Now, in order to have the time and the velocity in constant units, right, because our time was in seconds and our velocity was in miles per hour, it might be a lot easier to convert our velocity readings into feet per second so that we have time in seconds and velocity in something per seconds. So if you do the simple conversion, you get these numbers instead. Okay, now we can figure out how much distance was traveled in each of those intervals if we just assume that the velocity was constant over each of those intervals. So from 0 to 5 seconds, we just assume that this velocity was constant, and we have 25 feet per second times 5 seconds, the seconds cancel, and we get 125 feet. We covered 125 feet in those first 5 seconds. We can do the same thing with the next interval, and the next, and the next, and the next. You'll notice that each time, no pun intended, we take the velocity and multiply it by 5 because that was the size of our time intervals, right? Each one was 5 seconds. So velocity times 5, velocity times 5, dot, 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 dot. Add all those together, tells us that we traveled 1,135 feet. Again, an approximation. But couldn't we do better if instead of measuring our velocity every 5 seconds, we measured our velocity every second? And then every half of a second, every quarter of a second, and so on and so forth. And you can see that these distances will become more and more accurate because we have a shorter and shorter time span. So this average velocity over that interval is getting closer and closer to the instantaneous velocity. Hey, now we're starting to sound like derivatives. So we could have, before we decide to make our intervals smaller, we could have also taken each of those time intervals and multiplied them by the velocity at the end of the interval. So our first interval from 0 to 5 seconds, instead of using the 25, which was the speed that we calculated at the beginning of the interval, we could use 31, which was the speed at the end of 5 seconds. So it's kind of like the difference between doing these left-hand rectangle sums and these right-hand rectangle sums, and we can see that that gives us another estimate of 1215, and we know the actual distance should be somewhere in between those two. So in general, if we suppose that an object moves with some sort of velocity function, we'll call it f of t, and then we have these 2 points A and B, right, where t is in between A and B, and we know that the function f of t is greater than 0. That just means that the object is always moving in the positive direction. Just going to make it easier for the math, because when we move on to things like physics, we have to worry about negative velocities, meaning something moving in a negative direction. Okay, so we can take these velocity readings at different times. We can start at t sub 0, what's called t naught sometimes, and that's going to be A. And then t1, t2, all the way up to t sub n, which is just going to be b. So we're going to take that same interval from a to b and break it up into n many pieces, n many intervals. So you can see the correlation between the area problem here. And the velocity is going to be approximately constant on each of those subintervals. Because as the interval gets shorter and shorter and shorter, even a velocity that changes doesn't have an opportunity to change a lot over that small interval. So it ends up kind of seeming like it's constant. It's not, but it seems like it is. Okay, so if these times are equally spaced, then the time between each consecutive reading is always just going to be this change in t, this delta t, which is always just going to be b minus a over n, the exact same thing we did to find delta x. And so during the first time interval, our velocity is going to be approximately f of t0, and thus the distance traveled is approximately f of t0 times that delta t. And you can start to see, hey, this looks exactly like f of x sub 1 times delta x, or f of x sub 0 times delta x when we were trying to find the area. So we get these similar sums. F of something times delta something, right, plus f of the next thing times the same delta, dot, 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 dot. We get this same summation. We let I go from 1 to n of f of t sub I, or t sub I minus 1, depending on if we're doing left hand or right hand endpoints, right, times delta t. And we can see these two formulas are exact like the ones we saw before. And thus, we see that if we want to measure, or if the more frequently we measure the velocity, the more accurate our estimates will become. Just like we saw, the more frequently we measured the area of the rectangles, the more accurate the area under the curve became. So it should seem kind of plausible to you that the exact distance traveled is going to be the limit of these expressions. If we let n go to infinity of this sum, it's going to be the same thing as if we let n go to infinity of the other sum, right? This being left hand, this being right hand. And that's going to give us the distance. So we've now seen that distance and area under the curve end up having the same, roughly, formulas. And I'll put them here so you can remember what they were, and you can see the similarities, right? Here is our left hand one, f of x sub 0, right? Delta x dot 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 dot, which is going to become the limit with the sigma notation. If we did the intermediate points, it's the same idea. And if we write them in terms of, we have these. And you can see that the area, right, expressed three different ways. Rather, if we did a right hand, a left hand, or a somewhere in between, these sums end up looking just like the sums for distances. So the distance problem and the area problem all come down to the same idea. We're going to take a limit as n goes to infinity of a sum of a bunch of heights of the function times the change, right, the delta of the function, and as n goes to infinity, these deltas basically go to 0. Okay, and that's the beginning of the definite integral as introduced by the idea of area under a curve and distance of an object.